Hello everyone and welcome to part 2. This is a optimization video, and in the first part we looked at taking the derivative, just a few things in context, and showing why the time formula for Peter running and rowing was the value given, because we were given that function and we had to explain why. And I sort of did that for a bit of maths and just showing how we can calculate time relative to displacement and velocity. Okay, so we've taken the first derivative, and when the first derivative equals 0, then that means we have our minimum x length, as explained in the previous video. What I've done is I've gone ahead and I've just simplified it a bit. I had 17 over 17 squared before. Because this is the same as having 17 times 17, I crossed out the 17 there, crossed out the 17 there, so it's 1 over 17. So let's take 1 over 17 because, of course, it was negative before. And that's all I've done, and I've just cleared off the board because we got, more space that we need. Now, we set this to 0. So 0 equals half x squared plus 25 to the negative half, lots of, and I'll simplify here to 16x. Because, of course, we have 8 and 2x, and again we'll simplify that down further later when we can get rid of that half, but for the moment I'll just simplify those two, and that's all over 64, and that's take 1 on 17. Okay, and so from that what we can do is we can move this term to the left hand side, just so we can separate out the two terms. So we have negative half x squared plus 25 to the power of negative half, lots of 16x all over 64 equals negative 1 over 17. Okay, and so from that we have separated the two terms out, and I just realised I'm probably a bit wonky with the whiteboard there, but hopefully you should still be able to read it. Again, I am writing on an angle, so it is a bit more difficult. But anyway, from this, in fact I might actually kneel down and maybe I'll write straight. From this, what we can do is we can say, well, we can get this here. In fact, first off, no, we can actually get rid of the two negatives. Because this is negative on this side and this is negative on this side, we can times both sides by -1 and make them both positive. And that's probably going to be the easiest thing to do. Okay, and so from this, what we're able to do is we're able to go and times 16x by a half, and because we do that, we have 8x over 64, and from that we can actually go, well, that's x squared plus 25 in that function there, so because it's to the power of a negative half, we can bring it down into the denominator, where it will be to the power of a positive half. So we have 64, lots of the square root of x squared plus 25. Hopefully you should be able to see how I did that. Again, because it's negative half there, it's going to be positive half in the denominator. And now what we have is all of that equaling 1 over 17. So we just need to be able to simplify it here, and again, we should be fine. So hopefully you can read it with the green whiteboard mark there. I'll just make sure it's clear enough. But again, 8x, and in the denominator 64, lots of the square root of x squared plus 25 equals 1 over 17. So, it's positive half there, it's going negative half there, it's going to be a positive half when we bring it into the denominator. And again, this was times by that, so we get 8x. It's just simplifying, because keeping things simple is good. So we have, and I'll start up here, hopefully with a better whiteboard marker, 8x, and what we're going to do is we're going to bring the denominator term on the left hand side into the numerator on the right hand side. So we have 8x equals 64, and again we have 1 here because technically there's 1 in there, but it doesn't really matter. 64 lots of x squared plus 25 all over 17. Again, just move that from the denominator to the numerator as we swap the sides of the equation. Okay, and now what we can do is we can simply go 17 times 8, lots of x. Again, we're just bringing 17 from the denominator on the right-hand side to the numerator on the left-hand side. But 17, I'll make that a bit more clear by making a dot. 17 times 8x over, in fact, it wouldn't be over anything just, yeah, it would be over 64, because again, we can move the 64 back, because we want to isolate the x terms. So 17 times 8x over 64. And again, it's just a numerator-denominator switch. If it's in the numerator on one side, it's going to be in the denominator on the other side, and vice versa. And that equals x squared plus 25. Okay. And from that, 17 times by 8 is going to be equal to 100 and... In fact, I'll just double check, because it would be pretty bad of me to make a small arithmetic error. And what we get is with 17 times 8, 136. And then that's 136 over 64. That's lots of x. And that equals x squared plus 25. And hopefully you should be able to read that. Again, my whiteboard markers aren't the greatest in the world. But then we go 136 divide by 64 in order to simplify, and we get 2.125. So I'll write this here. 2.125, and that's the same as 2 and 1 over 8, because 0.125 is 1/8. So from that we can simplify this into a mixed fraction. So it's 2 times the denominator, so it's 2 times 8, and we get 16, plus the 1, because it's 1/8 added on, and we get 17 over 8. Again, keeping our answer exact as possible is going to be the most helpful. So we get 17 over 8x equals the square root of x squared plus 25. And from this, we are able to finish off and work out what x is going to be equal to. So we have this here. What we do is we square both sides, because when we square a square root symbol, the two operations sort of cancel each other out. So from that, we're going to just end up with x squared plus 25 on that side. So again, I'll write it here. 17 over 8 x squared equals x squared plus 25. And what we do is we times 17 over 8. What we do is we square that on our calculator. Whoops, and we make sure we have correct syntax as well. And we get 4.51. 4.51. Oh, 5. I'll just leave that 4.52. 4.52 x squared, again, because it's x, and we times every term. Imagine these as being two separate terms, but we times every term by 2, so we square that and we square that, so it's 4.52 x squared equals x squared plus 25. Okay, and hopefully I have almost, I've actually gone off the board there. Okay, so what I'll do is I'll actually rewrite this up here. And what we have is we have 4.25, as I said before, x squared equals x squared plus 25. And so what we do is we go, well, we want to get our x's on one side, so because this is positive x squared here, it's going to be negative on the other side. So therefore, 4.52 x squared take x squared equals 25. Again, I've just moved it from that side to that side, and then we simplify. So 3.52 x squared is going to equal 25. And then what we do is we take this 3.52 as a coefficient, and we move it from the numerator on the left-hand side to the denominator in the right-hand side. So we have x squared equals 25 on 3.52. So therefore we should have x squared equals, and it should be equal to roughly 7.11 from memory. So we have 25 divided by 3.52, and we get, 7.1. 7.10. I'll just leave it 7.1 though, go to one decimal place. And from that, to get x on its own, very simple the next step. Because it's squared, x squared, we just square root the left-hand side. So in order to square root the left-hand side, we just have x equals the square root of 7.1. So therefore, x equals, and we can just turn to our calculator to be able to square root it. And it gives us 2.67 kilometres. Okay, so 2.67 kilometres might be our minima, because again, we've gone through, we've set the derivative to 0, we found a stationary point, and from that, because there's a stationary point, we're able to go, okay, it could be the minimum x value or the maximum x value, and we just need to prove it using a sign diagram. So again, in context, the minimum x value will mean that Peter has to row and run within the least amount of time. Well, he doesn't have to, he will, I should say, because we're not imposing any restrictions on him. So again, x is some length, so if this length here is x, and that's 2.66 kilometres, if this is indeed the minimum, and the entire length is 6, so he will run, 6 take 2.66 kilometres, and he'll row the hypotenuse of that. Okay, so in order to prove that it's a minimum, we can clear off some board space and draw a sign diagram. So that's our one stationary point for this function. And what we can do is, again, we can just substitute in values to this equation, this original derivative. Because, of course, when the derivative is negative, it means that it's decreasing, and when the derivative is positive, it means it's increasing. So 2.67 is our stationary point, and what we're going to do is we're going to plug 1 into this equation wherever there's an x. So I'm going to go alpha alpha f1, and I'm going to go down to 2 on my calculator, and I'm going to get a fraction bar. And what I'm going to do is I'm going to type in bracket x squared plus 25 raised to the power of a negative half, lots of, and I'll simplify the end bit to 16x, and then that's going to be over 2, because of course this is a half there, and then that's going to be bracket 64, and that's going to be take 1, and then wherever we have an x, I need to put in 1, so I can easily go back and change that, so that's going to just be 16, and that part there is going to be that, and then that's going to be take, and of course, 1 over 17, so again, alpha f1, get a fraction bar, and this is, of course, is for a TI-84, and we get a negative derivative. And because we get a negative derivative, that means that it's decreasing. So if we were just to think about this in function terms, where's our x-axis, and our derivative is decreasing, and we have a stationary point around here. Now, it could be a horizontal inflection, in which case it could go down like that. So the minimum value could be around here. Or it could be a minimum, in which case this is going to be the minimum value because there's only one turning point, so we don't need to check our tail ends. But sometimes you do need to check your tail ends because there's multiple stationary points and it could come down again. But again, because our derivative only gave us one stationary point, and if this is a minima, as we're going to see in a minute, then we're fine and we don't need to check our tail ends. And then what we do is we just copy this function by scrolling onto it, pressing enter, and wherever there's a 1 now, except for the 1 on 17, I'm going to replace that with a 2. So it's going to be 16 times by 3, because now, I won't change it with 2, sorry, because that's below the stationary point. I'll change it with 3. But we just solve that, and we get a positive result. And of course, the positive result means that the slope is going to be increasing on the function afterwards, and again, this is our time function, so this is going to be a minima. And because there's only one stationary point, that's going to be the lowest value, and we've proved it. So from that, we know that this distance, when it's 2.67 kilometres, then of course Peter is going to have to row and run the shortest distance. Thanks for watching, everyone.